Really wonderful to be here. And I'd like to thank Rajesh, Gautam, Shiraz for organizing this. Uh, actually, this is, mm, let me say, I'm not going to talk about any one thing. I was rather confused as to what to do. So initially, I'll talk about what it was to talk working with Spenta. And then is more or less a report of snapshots of what I've been doing after that. So as I said, I think many of us here, we were students in TIFR when Spenta joined. Avinash, Sanjay, Sorendu, myself. So we saw the group before and after Spenta. And there was a huge difference. I think he made a big difference to the group. As everybody says, he's brought in a huge amount of energy, changed the type of things that were discussed, type of things that were done, and also changed the way the group interacted with groups outside, other groups in India. Now about me, I was actually at that time working on some PhD problem which was going nowhere, and I was bailed out by Avinash and Spenta, who I worked with them and this thing. So then I started thinking, okay, what have I taken back from Spenta? Meaning, so I think the thing is, he stressed that, at least for me personally, he stressed on this importance of building up a good physical picture. He used to keep saying this, well, in physical picture that you need, and away from not just the formulas and formalism, etc. And so that is something, I mean, it sounds a bit trivial because it's obviously so important, but it wasn't so at that time when we were PhD students. I mean, just to say what I mean, I think many of us in India, we sit on interview committees, we torture the applicants by asking them to plot graphs. And I think there'll be agreement that e to the power minus x is tough, x e to the power minus x is a killer. But it's not because those kids are dumb, they're all smart, I mean, they all this thing. Nobody taught them to visualize. Nobody pointed out that it's a good thing to do, it's a useful thing to do. And so I think again, but again, when somebody tells you to do something, the normal, healthy human reaction is to do the opposite. You have to be convinced. So let me say what convinced me. Those are the physics problems that we did. So this is my sort of topic of my thesis. This is one Avinash this is probably Spenta's first paper from TIFR. So, so in this, let me just give the background a little bit more that Nambu Jona-Lasinio model is a very old model. It was inspired by Nambu's work on superconductivity, where it described the U1 symmetry breaking. So he imported the idea into high energy physics, strong interactions, to describe chiral symmetry breaking. And so it's now in superconductivity, it's the electrons which pair up and form the condensate. Over here, the only fermions that Nambu knew of, this was in the 60s, Nambu knew of were nucleons. So he had massless nucleons, and nucleons and antinucleons paired up and condensed to break chiral symmetry. And so that was the model over there. Then later, actually in the 80s, early 80s, people started talking about the SCRM model. SCRM model is also a completely anachronistic model proposed in the 60s, as where the baryon was supposed to be a soliton in the theory of mesons. Because of its anachronism, meaning it came much before its time, nothing happened for a long time. Then in the early 80s, connection to QCD started. It became, there was this Largen paper that Avinash talked about. Then there was a thing that baryon current was topological. And so after all that, and what is impressive here is that the reinterpretation of the model. I think the fact that you replace quarks by, the nucleons by quarks, then everything makes sense in the model once you do that. But that physical, I think it required a lot of courage also, that physical reinterpretation, to take some old model and say, this is this thing. And so Then the rest of it was. Then this was again in this paper. This was a paper again which this mentioned. So this was again in that time. This result came out anomaly cancellation, and people thought that the gauge group was fixed to be these two SO32E8 cross E8. So there was a lot of revival in the string theory. This thing. Then it was also clear that you needed compact dimensions since the theory made sense only in 10. Then this paper of Nizhnik and Zhomlachikov came with current algebra. And I think when Spenta read it, he immediately saw a string propagating in a compact space. He realized basically that it gives you an explicit construction of a model in which you have a string propagating. From that idea to the papers, of course, a lot of work, and I think we had a lot of fun doing that work. But that physical picture was very, very important, very clearly. So I got convinced that, and studied it's important to make. Working on Nambu Jona-Lasinio model had also made me sort of familiar with superconductivity, and also that condensed matter, meaning field theory is field theory, you can apply it anywhere. Then there was also a lot of action occurring in condensed matter in the 80s. So Proiskin had come to TIFR, given a talk on sigma models and topological terms in quantum Hall effect. Bhaskaran had come and given a talk on gauge theory, confinement, etc. in condensed matter. So postdoc onwards, I switched to condensed matter. And this was one of the first pieces of work in the postdoc. Now this was based on, there was a paper by Polyakov, which gave a nice path integral representation for a fermionic propagator in 2+1 dimensions. So now this is the propagator to go from x prime to x. E to power minus m times length alone would have given you the standard bosonic relativistic particle propagator. He said you add this term called the Wright as writhing in pain. So it's supposed to give you how the curve twists and turns in the 3 dimensions. And and if you add this with this particular coefficient, this represents a fermionic propagator. So our contribution was, in his paper, it was not very clear where the spinor structure was. 2+1 relativistic thing means you need a Dirac equation. And so what we figured out was that lies in the initial velocity and final velocity. That is, the spinor polarization of the initially is the initial velocity, direction of the initial velocity, and the spinor polarization, the final state, is the direction of the final. So then we could, write explicitly fermion operators so that you calculate the correlation functions of this and you get a Dirac propagator. So again, even Nambu Jona-Lasinio model work, also this Bose Fermi duality is in a rough way this thing. So after this Bose Fermi Chern-Simons theory, etc., I automatically got interested in anions. And then Haldane had written a paper called, which generalized the exclusion principle. The idea was this, that if you take a single particle space with dimension d0 and you add n fermions, it blocks out n states. That's the Pauli exclusion principle. But suppose you had systems which block out only a fraction of those n states. Then these are the, what he called the generalized Pauli exclusion principle. And he gave a few examples where explicitly this thing occurred. Now, one question was, okay, there's a normal statistics, there's a exclusion statistics, are these two related? And so in these papers, we showed that they are actually related. And in fact, derived so that G is this alpha into 2 minus alpha for an anion gas, and also what was G for the quasi-particles in a Luttinger liquid, 1D massless field. And so the insight we took away from there is that what is happening in these cases, why is this dimension of the single particle thing getting reduced, is that when you add one extra particle, it interacts with all the other particles in the round and produces phase shifts and energy shifts which sort of flow off into infinity. it's very important that they flow off into infinity, that however high the extra particle level, it is still getting affected by the one guy you put. And so this kind of thing was very much in the air for correlated systems and non-Fermi liquids, etc. So I always thought that this will have a lot of application in that field, but somehow it hasn't. I mean, now I think if you ask a graduate student working in condensed matter physics, what is exclusion statistics? He won't know, he doesn't need to know. It's one of these very nice ideas which somehow hasn't proved very useful. Okay, so this is the most recent thing that I've done with, so Hassan is my colleague in math science, Archana is his student. So this is on the Hofstadter butterfly. So, so the system is just electrons in a plane, the standard quantum Hall system, in the presence of a periodic potential. So now there are two length scales in the problem. One is the magnetic length, and the other is the lattice spacing of the periodic potential. Now, when these two are sort of the order of each other, when they're equivalent to each other, that is what we call the Hofstadter regime. So this was studied by Hofstadter long ago. And if you plot the energy spectrum over here versus flux, so for different flux values, you just solve the single particle Hamiltonian, plot the energy levels, and you get this fractal. This is there's a self-recursive structure here, and it's a, so this created a lot of interest and continues to create, a lot of people are interested in it. A fractal sort of thing coming up in a quantum system. But also more interesting is that there's a new topological invariant as soon as you do this. As you know, in Hall, quantum Hall systems, there's a topological invariant which is identified with the Hall conductivity. And that's a Chern invariant, and that partially discovery of that had got the Nobel Prize recently. But now, when you add this periodic potential, there are two invariants, this T, which is the old Chern invariant, and there's another integer called S. And these two satisfy a Dampf-Dine equation, where this R by Q is the number of particles per unit cell, P by Q is the number of flux quanta passing per unit cell. Now, actually, this is what has, I mean, so recent, Hofstadter butterfly remained academic interest, but recently in graphene superlattices, people have actually experimentally found it, and that's why there's a revived interest in it. What they have actually found is this extra, so here, if you keep T fixed and vary R by Q, P by Q, you should get a straight line with slope equal to T and intercept equal to S. So that is what these experiments see. So there were several experiments a few years ago, almost simultaneous. This is one of them. So, this is what I was calling R by Q, particle density. This is the flux density. And here, and what the false color gives you is the Hall conductivity, or Hall resistivity is actually what they plotted. So you can see that you take these straight lines of the constant Hall resistivity. They intercept at 0, which is the normal Hall thing. But they found these two which have an intercept, non-zero intercepts. So this was discovered recently. The second topological invariant was experimentally seen. The fractal is actually impossible to see experimentally. I mean, that's why topological invariants have an importance, that they are robust quantities which can be seen in Excel. Now, what we have done is we have tried to look at the effects of interactions. And in a nutshell, we find a lot of topological transitions in the systems when you add nearest neighbor in we change the topological numbers, the Hall conductivity. And that results in the disintegration of this butterfly. So this is a non-interactive system, V equal to 4. It sort of disintegrates from the half filling outwards as you increase the interaction strength. Now, then after 2004 tsunami, where I was in Chennai during the tsunami, of course, so it was a huge event. And I started getting interested in the physics of it. Initially, it was just, we were interested in science popularization, and Awareness is supposed to be one of the things, protection against tsunamis. But then I met people from National Institute of Oceanography and got more professionally interested in it. One of the things we did was, so there was a paper in Science on this earthquake, and using oceanographic methods, they had said that this is the amount, this is the source. This thing is simply that you know the arrival time of the tsunami at different points. Then you can say, okay, if it arrived 157 minutes after the earthquake, where all could it have come from? The backward ray front. You look at the total this thing. And now, my colleagues in NIO noticed that this 45 minutes for Port Blair clock was wrong. It didn't match with the normal tides. So this we rejected, and then we had also data for Paradip, which is somewhere here. And putting that together, we extended the source and for 30. What I liked about this work was that, you see, it is, I think growing up in chaotic traffic helped. I mean, like in Europe or US, if the light is green, you go. Over here, even when the light is green, you look. There might be some idiot who's jumping the light. So even when they got the data, they checked. And that is what resulted in this comment. Then it's amazing, but before 2004, there had been no work on tsunamis in India. Tsunamis were in the oceanographers, internationally people had always been working on them. But after this NOI people realized that, this is an earthquake which occurred in 1945. I think you can't see it, this is the epicenter. It occurred on the shelf over here, where what is now Pakistan, and this is called the Makran coast. So this is often called the Makran tsunami. So now they were in Survey of India in Dehradun, the tide gauge records, because this is pre-independence, so all of it was, charts had been sent to Dehradun, of Karachi, Mumbai and Aden. Aden is somewhere here. So this is what the chart looked like. So they got it dug out, digitized, etc. And now there were several puzzles about this tsunami. That there were very persistent high waves in Makran coast. This is the Makran, Pasni, Ormara, the towns, but not at Bombay. Then Karachi had a lot of delayed high waves coming. So earlier people had said that maybe there were secondary earthquakes which caused these delayed waves. But our explanation, the main point is that the earthquake occurred on the shelf, which is not very common. So much of the energy got trapped over here. It came here, you see the depth of the ocean is something like refractive index for these water waves. So when there's a sharp change in refractive index, a large amount gets reflected back. So it bounced up and down over here, and that's why it remained here for a long time. And then it went here as coastally trapped edge modes, very similar to the edge modes of this thing. There are these solutions for the shallow water equations also. And so they went like this and reached Karachi. And of course, by the time it went to Bombay, everything had dissipated, so Bombay didn't see anything. Now, this is my end game. As actually David said, 65 is the beginning. I'm only becoming 60. But this is the beginning of the end game. End game can go on for a long time. So this sort of, you see, I've always been very interested in, love the mountains. This combines mountains and physics for me. So we studied this glacier called Satopan Glacier. It's one of the tributaries of the Ganga come from here. So I collaborate with H.C. Nainwal, who's in Srinagar University. Srinagar in Garhwal, not Kashmir. So this Srinagar is somewhere here. And Argo Banerjee is also a former physicist who's in IISER Pune Climate and Earth Science. So we are, interested in many things, but one of the main things is debris-covered glaciers. Many of the Himalayan glaciers have a thick debris cover. This shows Satopan, the glacier we are studying. All this is actually ice underneath. So this shows a cutout. You can see all mud, stones, rock, everything lying here. Then this wet part is where the ice starts. So there's a mantle of this debris on many of these. And you can see the ice only at the high altitudes over here in what is called the accumulation zone. Okay, this is my last this thing. So this is a process we are trying to mainly interested in, avalanche-fed debris-covered glaciers. These form about 20% of all the glaciers in Himalayas. So because there are two things, ice and debris, the dynamics is more complicated and has to be understood in order to predict the behavior of these. And because there are not very many of these things outside the Himalaya, it's not a very well-studied problem. And this is the main problem that we are going to. So we've set up an observational network, and what I'd like to do in the next few years is consolidate it. Because you see, there's all these things, you're studying climate effects, that's a decadal scale problem. So you need data at decadal scales also, you need to continue. So, so that's, thank you.